Okay, I have checked all the quiz. Later you can have your score. Since this is going to be last week for the course, so next week same time will be final. Okay. So next week final exam. Topics will be covering the high order and the Laplace. Okay. So I would like to just finish off what we can within this week. Hopefully, I can finish some parts of the Laplace transformation. So another example here that we can find is we can try to solve, especially the second order, okay? Especially the second order for Laplace using Laplace transform. So solve this y double prime minus 3y prime plus 2y equal e with power of negative 4t, and you are given the boundary, the initial value. Okay. So basically, we can start taking Laplace transform for each differential. So y double prime we can change, or if you want to write like step by step, we can write using Laplace each forms. Okay, and then we can transform the double prime become s squared and then ys minus s minus y prime 0 minus 3 multiply with s capital Y s minus y0 and then plus 2. This will be just ys equal e with power of negative 40 is s 1 over s minus 4, so s plus 4. Okay. And the next part will be solving for the capital Y. Okay. Solving for capital Y, and then we can plug in the y0 and y prime 0 using the initial value. Okay. So let's start. Substitute the value. So y0 is 1, y prime 0 is 5. Okay, I think we can write s squared minus s minus 5 minus 3 s ys minus or plus 3, and then plus 2. Okay, now we group all together the capital Y. This will be s squared minus 3s plus 2. And then the rest I will move to the right side. So this will be s, and minus 5 plus 3 is minus 2. Move to the right will be s plus 2 for this one. Okay. And then plus 1 over s plus over 4. And then we can solve this, divide by all with the s squared minus 3s plus 2. Okay. And then perhaps if we would like to make it all together within here, so s plus 4, s squared minus 3s plus 2, so s plus 4, s plus 2 is s squared plus 6s, right? Plus 8 plus 1, so plus 9. And then we need, I think, partial fractions to separate these big fractions. So we can factorize this, right? So s minus 2, s minus 1. So we have s plus 4, or maybe let me write with s minus 1 first. S minus 1, s minus 2, and then s plus 4. And then this will be A, B, C. And then we need to find the ABC. So we have A, s minus 2, s plus 4, plus B, s minus 1, s plus 4, plus C, s minus 1, s minus 2. This should be equal to the s squared plus 6s plus 9. Okay. Now we can let s any number, but to make it easy, we can choose the number that is in factors with all these factors. So we can try s equal 2, try s equal 1, and then try s equal negative 4 to get all the constant. So let's say s equal 2. So this will be 0, and this will be 6b plus, or maybe let me write here. So 6b equal, or 6b equal to 2 squared 4 plus 12 is 16 plus 9 is 25. So b is 25 over 6. And then try s equal negative 4. 0, 0, negative 5, negative 6 is 30c. And then this will be negative 4, 16, 16, negative 24 is 8, negative 8 plus 9 is 1, so C is 130. And S is 1. When S is 1, we have 5, negative 5a equal to 1 plus 6 is 7, it's 16, right? So A is negative 16 over 5. Okay, so we have everything now. So we can write that s squared plus 6s plus 9 over s plus 4, s minus 2, s minus 1. This equal A is negative 16 over 5. And then plus 25 over 6. And then plus 1 over 30. Okay. And basically, what we are going to do next is we take Laplace for each fraction. Okay. So take Laplace. So Laplace inverse. Okay. So let me write in the new space. Okay, let me resize this for a while. Let me resize. Okay, now we take the Laplace inverse. So this will be 16 over 5, and then Laplace inverse. This will be 1 over s minus 1 plus 25 over 6. Laplace inverse 1 over s minus 2 and plus another Laplace inverse. It's 1 over s plus 4. And since all is the same pattern and structure, we know that this will be the exponent, right? The exponent functions. So we are going to write the whole thing will be, so since this is the ys, the capital Y, so this will be, if we inverse that with Laplace inverse, so we have our solutions. This will be e with power of t plus 25 over 6. This will be e with power of 2t, and this will be plus 1 over 30 e with power of negative 4t. Okay, that's our solution. Okay, now if we move to some theorem is about the behavior for the f, the capital F of s. So if we have this, okay, see the function is a piecewise continuous and exponential order. Okay, if we take the limit as s going to increase, the Laplace for the f will be 0. So this will be, so I just copied this. So based on what we have here, using the comparison from previous part, so this is by definition, okay, by definition of the Laplace. So if we say that we are going to have this value of m, okay. So if we try to integrate this exponent, this will be the form, right? So I would like to just focus on this s minus c. So since this is using the improper integration, and since this s minus c, if you imagine that if we have like s, the s going to be larger and larger, the value of the Laplace of f, this will be going to be 0 because of this, the right side, okay? So if s is getting larger, so it will be m over infinite, or it will be 0. Or you could say this is limit, or maybe let me write with green, limit Okay, so the next sections will be another theorem about the translation. Okay, so next is the translation theorem. So let's start with the picture first. So if we shift our f of s, shift to the right some a units, so we have s minus a. Now we could start from the definition. So if, okay, let me write here. So if we have Laplace ft, we have capital Fs, right? This is our definition. Now based on this, if we have, for example, if we have Laplace of e with power of at, and then multiply with ft, by definition, I think I need to write a little bit smaller. Now by definition, we can start by taking the integration from 0 to infinity and then solve using improper integral. Okay, and we can combine this exponent, and you will see that we can make it into e negative s minus a t, okay, ft dt, which if we want to write by definition, this will be f s minus a. Okay, so basically if we have a Laplace, so, or maybe let me write an example or a conclusion. If we have Laplace of e at and multiply with the function f, this is actually the same as the Laplace of f, but then we translate s or shift s to s minus a. Okay, so this is another way to write Laplace, okay, using this translation theorem. So whenever you have e, so you have like e, maybe 2t, maybe the f will be sine, for example. It means that the same as Laplace of that sine, and then the s will be translated or shifted, becomes s minus a. Okay, so for example, if we take L, so example, let's say e 5t and then t cubed. This will be the same as Laplace of t cubed, but then we changed or shifted the s to s minus 5. So the t cubed is 3 factorial, right? And then over s with power of 3 plus 1 is 4. Okay, and then we shifted s become s minus 5, or this become 3 factorial over s minus 5 with power of 4. So in another word, this e symbolize how the Laplace of the function beside the e will shift it. Okay. Or you can write the conclusion as follows here. So if Laplace of f is a capital F and a is a real number, then if we have this Laplace with e with power of at multiplied with f, it becomes the capital F and then s minus a. Okay. Now every Laplace, we must have the inverse. So we also have the inverse for the translation. So can we inverse from here to this part? Okay. So we can actually. So we need to write the inverse form. I think let me make it bigger here. Okay, and I think I will move to maybe just below here. So this will be the inverse form of translation. So basically we write L inverse so let me write one by one. This means that this is Fs, and then this will be s minus a, right? And this is equal to e at ft, where the ft we get from Laplace inverse of the Fs. So it's a little bit quite long. So let me just give you an example. So example on how to use the inverse. For example, if we want to take the inverse form of 2s plus 5 s minus 3 squared. So this basically we need partial fraction. So let me write partial fraction here. S minus 3 squared. Remember, partial fraction, we take, if we have multiplicity, we can make this become s minus 3 and s minus 3, the second one is squared. So we have a constant for both of these fractions, right? And then we can basically write down the formulations as this. So as minus 3a plus b equal to s plus 5. So a is 2 and negative 3a plus b is 5. So since a is 2, so b is 11. So we can write Laplace, or maybe where's Laplace? Laplace inverse of 2s plus 5 over s minus 3 squared. This will be 2 and then Laplace inverse one over s minus 3, and the other part will be 11, and then Laplace inverse and then 1 over s minus 3 squared. Now, if we look here, I think the first one is easy to follow. It's just 2, and then we know that this will be E. Now, the interesting part is this 11 part here. So we can write that, or maybe let me write this a little bit down here, and let me write that the Laplace inverse of this 1 over s minus 3 squared, we can think this as Laplace inverse of 1 over s squared, okay? And then shift it from s to s minus 3. Okay, 1 over s squared is from t, right? From t. So this will be t. So this will be, let me write different color. So this will be t, but then we shift it to s minus 3, which means that we need to multiply t with e, 3t, and t. Okay. So this 11 part here will be multiplied with e, 3t, multiplied by t. Okay. So basically, if you have some function that you can, like for example here, we can think basically before it was shifted, like this is 1 over s squared. What kind of functions if we take the inverse? And then how do we make that shifted 3 units? Then we need to multiply with the e. Okay, now another example on how to use this, the translation inverse. Okay, so let me go through one more example. So if we have a Laplace inverse, this will be s over 2 over here, and then s over 3. This will be s squared plus 4s plus 6. Okay. Okay, now how to start this? First is maybe if we take observation on the denominator. Can we factorize this? Can we? No, right? So, but we can complete the square, right? Sometimes when we complete the square, you will see something that is having squared plus or minus something, right? And we can imagine that this complete square is a result after it was being translated or shifted, right? So let me start with this. We can make a perfect square if we take this. So this will be x squared plus 4s plus 4. So we need to plus 2, right? We can make it like this. Okay. So perhaps we can write this will be s plus 2 squared plus 2. Okay. And we need to also look on the numerator. Okay. Can we factor something out of this numerator and taking s plus 2? So if we take, for example, if we multiply the, like, we have half let me write here, maybe here. So half s plus, oh wait, maybe you make it not clear. This is 5/3 and this is s. Okay, to make it clear. So if we make this, if we change s to s plus 2, so it becomes half s plus 1, and we need to make it into 5/3. So we need to plus 2/3, right? So let's change the numerator with this. So half s plus 2 plus 2/3. Okay. And now we can write half and then Laplace inverse, and the top will be s plus 2. I will make it into two fractions. This will be s plus 2 squared plus 2. The first one. The second one, 2/3. And then Laplace inverse of, we have 1 over s plus 2 squared plus 2. Okay. And now we see that we have s plus 2, s plus 2, s plus 2. So we can make some prediction that this is the result after we translate with 2 units and with 3 units. So we need to, at the end, we need to multiply with e with power of 2t. But we need to know what kind of Laplace that brings this together. And the possibility is when we have something here and then the below is the s squared plus constant, either the numerator can be s or can be a constant. It's either sine or cosine. Okay? And the next thing is we need to manipulate all the structure here to make it clear that it is sine and cosine. So first we can think that this will be half Laplace inverse, and we can think before it was translated it was just s, and then s squared plus 2, and then this is supposed to be s goes to s plus 2, right, after translations. And the same thing with this, so 2/3. And then Laplace inverse. This is, we have s squared plus 2. And let me shift this to the left side. This will be s to s plus 2. But of course, for the constant, we need to have the square root of 2, right? So we need to have square root of 2 here to make it clear that this will be translated into sine, right? And then we need to also multiply with square root of 2 here to make it balance. Okay? Now, because of this, then we can now for sure say that this will be our cosine, and we need to multiply with this. The translation will be e with power of negative 2t, right? So half e negative 2t, and the function will be cosine square root of 2t, okay? And then plus 2 over 3, the same translation, e, or now is supposed to be the square root of 2, sorry. E negative 2t sine, and that's our solution. So whenever you find some structure that you can think that it is as a result from translation, then the way you inverse, you can think the original forms and then multiply with its translation. Okay. You mean zoom out like this?
Yeah.
Okay. Okay, any question from the inverse of the translation? So basically, the exponent that we have defined in the Laplace is basically our translation factors. Okay, so if you multiply some functions with e with power of some at, it means that you are shifted with that a units. Okay? You shift the graphs with a units. Okay? And in other words, whenever you solve using Laplace transform, and when you are going to turn back into the original equation, which you need the inverse, you can use this inverse on translation into your solution as well. And I think it will be much like it will help you to simplify an equation that perhaps you can think this that the structure itself, like for example, like this one, if we don't know how to use the translation, we are going to be a little bit complicated here. We have s plus 2 and then s plus 2 squared plus 2, right? This will be, and maybe you will expand this and then it will be really maybe long in your notes. But if we think from here, s plus 2 and s plus 2 squared here, perhaps this is like after we translate, after we shifted the graph. So we know that, okay, let's say we have this just s and s squared, and we know that this will be the cosine functions after Laplace. And then we shift units of 2, right? So next section, we are going to move to the unit step function. Okay, unit step function is another function that I think for engineering purpose is really useful, especially if it is related to power or electrical. So we call this the unit step function. Okay? Or we call this a Heaviside function. Okay? So the definition, the happy side or the unit step function, we have usually how we write a function is with the curve u, the unit step function, t minus a. It can be 0 or 1. Okay? I think you'll see this in calculus, right? So we say this is 0, it starts from 0 to a, according to this relation. And then when t is greater equal a, it will be equal to 1. So we are going to have something like this, as in our graph. Okay? So stay 0, and then after the some point here, it will jump here. Okay? To make it maybe make sense for what is the purpose, it's like when you turn off your lamp or turn on, like it's jump, right? It starts to go turn on or turn off. Well, it's kind of similar. Okay, so that's how this is pretty useful in, especially for electric, for electricity. And if you see another example here, on the right side, you see here, we have another happy side. So happy side is 0, and then it's jump, and then it's going to be in a line equation, which means that this line equation is 2t minus 3, but our happy side that make it 0 is this happy side or unit step function t minus 1. So because this is in 1 here. Okay. And there are another statement for the happy side. So we can write this. Let me make it bigger. We can write this. You have a piecewise, two functions g and h, and for the function g, this is the one that making 0 for the happy side. So we are going to have g of t minus g of t, and then multiply with the happy side t minus a, and then we plus the h of t, and then multiply with the happy side. Okay. And similarly, if we have let's say we have the 3 piecewise, and we have not only one constant but 2, we can write, if this is 0, and then we have a function of g, and then 0. So we have, first is number a. Okay. So we have a, and then we have an interval from a to b, and then we have interval after b. Okay. So we can write g of t, and then we multiply with the happy side t minus a, and then minus happy side t minus b. Okay, so I think perhaps some of the example here that I can show is this one here. I think it's better to look at the example. So this start from 2. Okay, start from 2, and then minus 3. Okay, so minus 3, so it's minus 1, so it's going down. And then we start taking t minus 2 because we start from here, and it's going down here. Okay, so and then we see that after some interval, and then at t equal 3, it's become another a 0, right? Another 0. So basically, what this does is whenever you have the happy sign, that will be taking your functions to these positions. Okay. And of course, the heavy side also can be can be related to the Laplace as well. So if we have this part here, so whenever we have if we define our Laplace, okay, with that, so if capital Fs is Laplace of the function t, then if we have a function and then multiply with the happy side, then we are going to have e negative as and then capital Fs. Okay, so we have the exponent. So here is how it looks like as in the graph. So we are basically, this is another translation. So another translation with the unit A. So this is a translation with unit A. So maybe I will write some notes here to make it why it's that happen. So because if we take Laplace, so we take the integration from 0 to a. This is e negative STF. Let me write a little bit. Let me make it smaller. And then plus, so from 0 to a and a to infinity. And based on the piecewise, this will be 0 for 0 to a. And this will be 1 for t greater equal a. This is just stated that this part will be this. Okay, this one will be our. So this is equal. I think we can have a break and I will continue this. Okay, let's finish off this part. So I think we can start by taking the substitution for t minus a to make it simplified. So if we have t minus a, so dv is dt, and also t is v plus a, and we can change everything. So we can change that. This will be, let me write here, so Laplace and this simply become e power of negative as, and then multiply with Laplace of function of t. So this is Laplace of the ft minus a multiplied with the Heaviside function. Okay, so if we identify the f of t, let's say it's just 1, then f t minus a is 1, and f s will be Laplace of 1, which is 1 over s. Now we can have Laplace of the Heaviside t minus a. Only with this Heaviside we can have e, and Laplace of 1 is 1 over s, so multiply with 1 over s, or divide by s, like that. Okay. And of course, every Laplace has an inverse, so we can also write an inverse form for this Heaviside. So the inverse form of the function of Heaviside. So Laplace inverse of e with power of negative as of fs equal ft minus a, and then Heaviside t minus a. So the goal for the inverse is to convert from the s to t. So for example, if we take the Laplace inverse of 1 over s minus 4 multiply with e with power of negative 2s. So we know that this negative 2 will be, or because it's already in negative, so we'll have to focus on the fourth 2. This is a, right? And this will be f. Okay. So we are going to have a multiplication of e, because it has a is 2, so we could start with t plus 2 or maybe let me write first Maybe let me make it a little bit smaller. Okay, remember that if we have the Laplace inverse of the 1 over s minus 4, this is equal to e with power of 4t, right? And we multiply this s 1 over s minus 4 with the e with power of negative 2s, which means that we are going to shift this through t minus a. So we are going to have e 4, and then t will be becoming taking from the 2 from the 2s. So this will be t plus 2, and then half the side of t minus 2. So this will be f of t minus a. This will be the half side t minus a. Okay, maybe another example. Let's see if we have Laplace inverse of s over s squared plus 9, and then we multiply with e, negative p pi s over 2. And then we identify first that this is the fs, and this will be the a, or a will be pi over 2. Okay. So we are expecting we have some shifted with a pi over 2. We can first try to find the relation. This is cosine, right? With the 3 squared, so this is 3t. So this will be equal to cosine 3, and then t minus pi over 2, and then half side t minus pi over 2. Okay, there are another way to write the Laplace of this Heaviside. Okay, so we have now here is f t minus a Heaviside t minus a, right? So how about if we just have this is just a function of t without any t minus a? We can also write and we can exchange the form using that form. Okay. So suppose we have this is alternative form. So let u is t minus a and t will be u plus a. So we can write the Laplace. Let's say we have g, and then we have the Heaviside function t minus a, like that. And then we can break down the formulations as e negative st g of t dt. And since we have the substitution, we can substitute the t with u plus a. So e negative s u plus a, and then g, this will be u plus a, and then du, and it's changing from 0 to infinity. And this part now we can write directly that Laplace of g of t this is equal to e negative as, and then Laplace of g t plus a. So basically, this can also help to solve some solutions. For example, if we want to take Laplace of t squared and then Heaviside, and then t minus 2. If you want to change this t into t minus 2 and then using some algebra and make it into like different structures, it will take time. But using this Laplace here, we could directly write that this will be equal to, we can Laplace the t, okay, this t, and then we have a, which is 2. So we can take the t plus 2 for this Laplace here. Okay, so we can make this as e, directly e, and then negative a is 2, so negative 2 s, okay, and then Laplace of, we have t squared, so t plus 2 squared, and then that's it. Or if we want to take the expansion, we can take t squared plus 4t plus 4. So we take Laplace each component. So e negative 2s, this will be 2 over s cubed, this will be 4 over s squared, this will be 4 over s. And I think we can just stop until there. Another example, if you have Laplace of cosine t and then heavy side t minus pi. Okay, so we can identify, here is, we have s is pi, so we can write e negative pi s and then Laplace of cosine t plus pi, right? Now, for this cosine or sine, that we have sometimes having this plus pi or a negative pi, or we have some shifted in this t inside here, we always remember that in trigonometry, this will be the same as it's if we have the cosine t plus pi, the value itself will be the same as cos t, right? The differences will be the sign. Okay? So we can write this as negative cosine t, right? So we can write this as, or let me write here that the cosine t plus pi is negative cosine t. Right? So we can write this is become negative e negative pi s Laplace of cosine t. So cosine t is negative s over s squared plus 1. So we can write here, and this will be s squared plus 1. Okay, I think I can give you another example. Actually, my plan is to give another one more like sections about the transform of derivative and integral, but I think maybe we skip that. Okay. So let me give you an example first. So solve y prime plus y equal f of t. So we have this, okay? So the f itself is a piecewise of 0 and another function of cosine. So we need to define first what is the f, okay? So remember f, if you have any piecewise and one of them is 0, it could be the Heaviside function. Okay? So we can write this as the unit step, okay, unit step function. So technically, we can write the f 3 cosine t and then multiply with Heaviside. And then we can take it into our general solution. And then take Laplace both sides. So as usual, remember, we take Laplace, solve the algebra, solve for the capital Y of variable s, and after we get the equation, we go back to the inverse. Okay, we turn back into the t, okay, to find the solution. So let's say we have here, we take Laplace, this is s, and then capital Y s minus y of 0, right? And then plus, this is going to be capital Y s. And then Laplace of this will be, this will be, the function is cosine, so s over s squared plus 1 cosine t. And then we have 3, so negative 3. So negative 3 s over s squared plus 1 and e negative pi s. With the same reason as we mentioned before. Okay. So this will be s, this will be minus 5 plus ys, or let me write directly here, ys s plus 1, this will be 5 minus 3s and then we need to solve this. Divide all with s plus 1. So we need to take the partial fractions. Let me maybe write on the right side. So let's say we have s and s plus 1 and s squared plus 1. So we have s plus 1 plus s squared plus 1. So this will be a, this is b, s plus c, right? Okay, so this will be a, s squared plus 1 plus b, s plus c, s plus 1, this should be equal to s. And then this will be bs squared plus cs plus bs plus c equal s. S squared is a plus b plus s b plus c plus a plus c equal s. So b plus c is 1, a plus b is 1. A plus c is 0. And from here we can minus that c minus a. Oh, this will be 0, sorry. C minus a is 1. So a minus c is -1. So plus this, we have -1. A is -1/2. C is 1 plus a, so 1 minus half is another half. And b is half. Okay, so a, b, c we get. So -half over s plus 1 plus bs is half s over s squared plus 1, and then plus half over s squared plus 1. Okay, we have this all three, and we factor half, so we are having 3/2 over. So 3/2, this will be -1 over s plus 1 e negative pi s plus s squared plus 1 okay. So each one of them we need to compute. So we need to take Laplace inverse, okay, for each one of them. So Laplace inverse for 1/over s plus 1 e. I think let me write one by one to make it easier. So this will be equal to, we can imagine that this is the ft, this is fs, right? So we can imagine this is start from a translation, okay, or e, right? This is e translated to t minus pi. This is a, right? And then happy side t minus pi. And then the other part, this is now is for 1 over s squared plus 1 e negative pi s. With the same reason, the a is pi, so we have, this is the fs, which we know that this is going to be the sine, right? This is sine t minus pi, and then this will be happy side t minus pi. Okay. And then last one is the s, which is related to the cosine. So we take Laplace inverse, so let me write here. So we take the inverse, Laplace inverse, become y of t. This will be 5e with power of negative t for the first one. And then multiply with 3 over 2. So plus 3 over 2 e negative t minus pi, heavy side t minus pi, minus 3 over 2 sine t minus pi, heavy side t minus pi. And then the last one is also minus 3 over 2 cosine t minus pi. Or if you want to write using the shift trigonometric, the sine t minus pi and cosine t minus pi, we can write as sine t and cosine t, but positive and negative, right? We can write the y of t, and maybe taking the 3 over 2 factors. And then the sign will be negative, right? So negative, so positive sine t, and negative become cosine t, and then multiply with the heavy side of t minus pi. And based on what we have here, since we define the function of t as a heavy side, so we might write our solution as two piecewise function. The first one is only this if we have only for 0 to pi, okay, and if it is greater than pi, we have all the heavy side. This is when t is greater or equal pi. So I think the topics will up until here. So next Thursday we are maybe having some exercise, okay? Especially for the last one. Complicated, right? But the idea for Laplace is still the same. What you need to do for Laplace, you have differential equation, you turn in using Laplace, solve for the capital Y(s), and then turn back with the inverse. And inside those process, sometimes you have to identify the functions, right? And if there is some translation, if there are some happy side function as well, you need to describe everything that you can find. And usually we need some partial fraction in between. So I hope you can review that part as well. And here is the quiz.